All right, so this is the lecture for the second part of chapter 7. And so last time when we finished with chapter 7, we had just finished talking about how electrons all talk about probability. So when we talk about orbitals, it's not that they really travel along in this ring going around them, but that there's a probability that they exist inside of that ring, right? Inside of that orbit, right? And so one thing is that all of this has to deal with electron energy, and that's why we care so much about where they're positioned. Right? So electron energy and position are kind of complementary. So the amount of kinetic energy they have is given by how close or how far away they are from the electron or the nucleus itself. And then from there also the speed that they're traveling when they're not attached to an atom. Right? So for an electron with a given energy, the best we can do is describe a region that it has a high probability that it's going to exist in. And so many of the properties of the atoms are related to the energies of these different electrons. So where electrons are, how many electrons there are, tells us about the energy that they have, and that's giving us some information about it. So this is an example of the different energy levels inside the hydrogen atom. Right? And so when you're in the first orbital, on average, we think that the electron should have this amount of energy associated with it. This has to deal with how close they are to the nucleus, so about their attractive force that they feel from the nucleus. And since electrons are traveling at the same speed, right, we're thinking that they travel at the speed of light because there's electromagnetic radiation, then we treat them the same. So the farther up they go in their energy level, you can see that the less negative they are, and so the higher their energy is. So the higher your energy level, the more energy your electron has. And so as you can see, they basically start at a negative number and they get less and less negative as they go all the way up. And so the idea is if they were to move all the way to the very top, so the farthest energy level possible, so our infinity, then our energy will be coming up to 0. Now this really means that this electron is just breaking free of our atom. And so that's why it's at that value of 0. I like to imagine it that our energy levels are kind of like the electron falling into a hole. Down at the hole is the nucleus attracting the electron. Up here is 0, right where they're on that cusp. And so the farther in the hole you fall, the closer you are to the nucleus. The higher up in the hole you are, then the higher your energy level. Now, that process, it gives us an energy. And that energy is tied into the principal quantum number. So the energy of an electron in a particular orbital corresponds to its quantum number, n. Now, all of this is tied up in your energy value given down here. And the thing that you want to pay attention to is you want to look at your constant here. This is called Rydberg's constant, and that varies for each element. And this n is your energy level. So the larger value of n, the more energy that electron or that orbital has, and the more energy that electron in those orbitals will have. And as you go more and more, right, then you're getting closer and closer to escaping, which is where your E equals 0. And so that's kind of our relationship between those two things. And so one of the things that we're going to look at is we're going to look at the wavelength of light for a transition in the hydrogen of an atom. So right now what we're saying is that we have an electron that's making a transition from n equals 6 to n equals 5. So it's going from a higher n to a lower n, which also means that we should be losing energy. So that delta E of our electron is going to be equal to the energy of the photon that gets emitted. So if you imagine, if this was our nucleus with our rings, right? Let's say that this is n equals 5, and this one's n equals 6. As our electron travels, it starts over here, and it's moving down to n equals 5. And when it does that, it's got to release some energy. And so it's going to release that in the term of a photon, or in the form of a photon. And the energy of that photon is going to be equal to that distance in the energy levels. Let's go ahead and clear this. All right. So our setup is going to look something like this. We're looking for that wavelength of that emitted light. Now, for us to find that is we have to look at our energies. So there's kind of like two equations that we're looking for. One is we know that there's going to be some energy change for that of our electron. And we know that the energy change of that electron is going to be equal to the negative of the energy of the photon because we're emitting it. And we know the energy of a photon is that one there. So we can put these two things together. We can find the energy change first of our atom or of our electron, and then we can use that to solve for the wavelength of our photon. So our first part is let's figure out how much energy we lost when we go from 5 to 6, or from 6 to 5. So we're going to take our energy of our 5 minus the energy of our 6. So we use our equation that I just showed you with Rydberg's constant for hydrogen, since this is a hydrogen atom. If it was a different atom, I'd have to give you a different constant. But in general, we almost always work with hydrogen because the model that we're using works best for hydrogen. So we get our energy of our 5 versus our energy of our 6 energy level. We subtract 6 from 5 since we're going from 6 to 5. So this is our initial, this is our final. And we get this expression right down here. We can find that energy in joules since this was in joules. And that's the energy change of our atom. Now I want you to take a moment. I want you to look at this equation right here, because you see that this is the one that I have on your guys' equation sheet. Now you can see it kind of in two ways. One of them is you have your initial minus your final, or you have your final minus your initial. It all kind of depends on how they, what this constant is that they give you. If they give it to you as a negative, then it's your final minus your initial. If they give it to you as a positive, then it's your initial minus your final. So I give it to you that the delta E for your atom or your photon is going to be equal to the constant 1 over your initial n value squared minus 1 over your final n value squared. Now this constant that you get is positive, so 2.187 times 10 to the negative 18 joules. And in this case, our initial would have been 6 squared. Our final would have been 5 squared. And the reason why I give it to you this way is that when your delta E is negative, it means that we should be emitting photons. If your delta E is positive, it means that you are absorbing photons. So I'm giving it to you in the setup in your equation sheet, so that way they line up correctly, that a negative one is emitted, a positive one is absorbing. Otherwise, in your book, just like how they've given it here, they've given it for specifically an emitting photon. So it just depends on what setup you're using. So now we have the energy of our atom, and we know that that's going to be equal to the energy of our photon, except the negative. And so we can plug that into our equation, just like we did last week. We use our Planck's constant, 6.626 times 10 to the negative 34 joule seconds. We use c, which is the speed of light, 3.00 times 10 to the 8. And now we can use our new energy to find our wavelength. And often we're going to change that wavelength into nanometers because that's our visible spectrum. And that's all we need to do. So just remember that 1 meter is 10 to the minus 9, oh, not minus 9, 10 to the 9 nanometers. And you can have the conversion between them. So we can check our units. We want to make sure that they line up. You can try this again. You can try this for n equals 3 and n equals 4, going to n equals 2, and both of those should lie in your visible range. So that means that they lie somewhere between 400 nanometers to about 800 nanometers. You can also look at what it looks like if you went from n equals 2 to n equals 7. You can do that comparison. So those are both practice problems that I would definitely recommend that you look at. Now, sometimes you can actually eject an electron. What that means is you've excited it so much that that energy has been able to break through from our electrons. So we can give that electron enough energy to break away from the photon or from the nucleus that's attached to. And so in order for us to do that, we have to be able to break past what we call the binding energy. So it's kind of like that energy tying that electron to that nucleus. Now, a shorter wavelength means that it has a lot of energy. And so if we use a very short wavelength, we can actually apply enough energy to that electron that we can get it to escape from the atom. Now that excess energy, whatever there was that was extra, that turns into the kinetic energy of the electron. So that goes into the electron and it transitions it from being inside that atom to being this free electron, and they'll be moving at that amount of kinetic energy. So suppose that we have a metal and it's going to eject things from its surface when struck by a yellow light. If we use an ultraviolet light, we're trying to think of what wouldn't happen. And so we want to think about this. If this is our electromagnetic spectrum, and this is our wavelength, our yellow light might be over here. Now it has some number of nanometers for its wavelength, and we want to think about how that compares with our ultraviolet light. Now, one way to remember that is that Roy G. Biv, which is your colors of your rainbow, right? So we have red, orange, yellow, green, blue, indigo, and violet. Right? And the interesting part about that is that actually corresponds with their wavelengths, and it gives us an idea about their energies. So red is our longest wavelength, whereas something like violet is our shortest. So if we wanted to think about it, ultraviolet is going to be down here past violet. Infrared will be up here longer than red. So if we wanted to compare our yellow here against that of our ultraviolet, we should be able to compare that. So we know that our ultraviolet has a smaller wavelength than our yellow light. And so I want you to think about what that means for your answer. So if we have a smaller value than, or smaller wavelength than our yellow light, we should have a higher energy. So if we can eject an electron with yellow light, we should definitely eject one with ultraviolet light. But the difference is that we should have more energy. In the same way that when we went back, the extra amount of energy from that photon, anything more than what it needs to be ejected goes into kinetic energy. That's the same thing for here. Oh. So our electrons would be ejected. and then they would have greater kinetic energy than those ejected by yellow light. And so this is the answer that we're looking for. So this is that same concept of what's going on, right? A particle that has more than enough energy to eject an electron from a metal surface, that extra energy, where does it go? Do we eject a second electron? Do we reflect it back to its source? Do we bombard particles? Do we give it kinetic energy? Where does it happen? And so that extra energy, it always goes towards that energy of the electron, its kinetic energy after it's been released. And so this is the beginning part of our quantum mechanical model, right? And so we're using this Bohr model for now. Now the problem with it is that Bohr's model actually only works for hydrogen. And it has to do with the electrons, right? And so while classical physics talked about that the electrons would fall into the positively charged nucleus, Bohr just said that they wouldn't. He said that they fell into that staircase, right? That quantized value. And so he said that they couldn't fall into them, but he didn't explain why. The other part about it is that circular motion, right? The electrons moving around in those orbits is not really wave-like. We don't really see waves when they move around like that. Waves don't always move in a circle. And so it wasn't sure about how those things work together. But what we do want to remember is that it's true that electrons exist only in these discrete energy levels. They can only have these certain values. And that those are going to be described by some set of numbers. The other part is that electrons, their energies, when we transition from one level to another, that comes with an energy involved, some energy transition. So we can't just freely move from one energy level to another. There has to be a transfer and exchange of energy as we do that. And so that was the second part. Now, there was a scientist that came afterwards, and his name was Schrödinger. And Schrödinger developed an equation to calculate the probability of finding an electron. So just how we had those orbitals, right? Those concepts of, well, there's a chance that the electron is going to be in this one. Schrödinger developed an equation to determine that, to give us a plot of where those electrons are going to exist. Those things are called wave functions, right? And they look like this symbol psi. Now I want you to understand the concepts of it. We're not going to solve wave functions. That's not something that you have to do for quite a while in your chemistry career. But I do want you to know about what the concept is. So that way, when I give you this next part, these quantum numbers, they're going to correspond to different shapes of that wave. And I just want you to be able to tie those things together because I think it's a little bit easier to understand why we get these numbers and why they can determine what kind of electron we have, because they're all giving us characteristics of it. So when we plot our wave function squared, so that way it's a positive value for an orbital, or sorry, when we plot the wave function against the distance, we're going to get the orbital, which is the probability distribution for the region where we're going to find that electron. So when we look at these wave functions squared, and we plot them against the distance away from the nucleus that they should be, we can kind of get an idea about what that orbital shape and value should look like. How far away from the nucleus are they? Now, there's a couple of different parts that determine that wave. So there's the size of it, the shape of it, and its orientation as we look through them. Now, those three things, we're going to tie them in with our, what we call principal our quantum numbers. And so our first one on that is our principal quantum number, n. We also have an angular one, L, and we have a magnetic one, m sub L. And these three things kind of tie into the three parts of our wave function. Our n is related to our size, our L is related to our shape, and our m sub L is related to our orientation. So we can use these three quantum numbers to kind of give us an idea. So the first quantum number we've already talked about. It's our n. And so our n value, that same energy level that we were talking about with Bohr's model, that is going to always be what n is talking about. So our principal quantum number, that first one, n, is talking about your energy level. It's the distance you are away from the nucleus. So it's your size. The larger the n, the farther from the nucleus you are. Now our next one is going to be L. Now our L is called our angular momentum, right? And that's a fancy word for basically talking about the shape that our orbitals are going to take on. Now some of them are going to be a simple shape. They're going to look like spheres. Other ones are going to look like balloons. Some of them are going to have like a dumbbell, or some of them are going to have these rings. And so what we want to think about is anytime we're looking at the shape of those orbitals, it's always going to turn into this L. Now, our n value can go from 1, 2, 3, all the way up, right? So we always start at n equals 1. That's our lowest value. And we can increase by them in an integer, right? So only whole numbers as we move our way up. There's no n equals 1.5, right? So you go 1, you go 2, you go 3, 4, all the way on up, right? Now, this is different for our L. Our L can have both positive values and negative values. So it's kind of bracketed in there. If our n has a value of 1, our L is kind of a bracket around there. It's tied at n minus 1 all the way over to n plus 1. Oh, sorry. It's not tied, not n plus 1. It's tied in there from 0 as its lowest one all the way up to n minus 1. So it's increasing as we go through that. So our bracket goes from basically 0, which is the lowest value L could be, all the way. So when n equals 1, our L value only has the option of being 0. When n equals 2, our L can be 0, but it can also be 1. So with each energy level that we add on, we get different shapes that can come into it. And so the 4 shapes that we're going to look at is S, P, D, and F. And so we're going to walk through those next. So our first one is when L is equal to 0. So every principal energy level, so that means every n value, has an L equals 0. It's the lowest energy orbital, and it looks like a sphere. Now this number of nodes you don't really have to worry about yet. It basically is talking about our options. How many different L orbitals shaped like a sphere are there? And there's really only one. So we only have one orientation for it. So L equals 0 takes on this shape. Our next one is our L equals 1. And so these are our p orbitals. Now we're going to come back and we'll talk about our m sub L in just a second. But I just want you to show what our p orbitals look like. And they look like these dumbbells. So our p orbitals have these kind of shapes. So instead of being like a sphere, they really have 2 different kind of balloons attached in the middle. Now, when we're looking at this, you can see that now instead of only having one option, we have 3 options. And so we need another number to tell us which one we're talking about. Are we talking about the one that's laying on its side, the one that's laying front and back, or the one that's standing tall? And so this is where our next quantum number comes in. And that's going to be our m sub L. Right? So m sub L is this right here. And it's giving us the direction or the orientation in space of the orbitals. So it's telling us, is it lying on its side? Is it standing tall? Is it lying front and back? It's giving us that orientation. Now it has a bracket and it stretches down from minus L to L. So when we look at L is equal to 0, then our m sub L could be minus 0 or positive 0, so just 0. When L is equal to 1, so that's when it looks like a dumbbell, then m sub L can be -1, 0, or 1. So it's got 3 options. So you can kind of imagine that this was our sphere up here. And when we look at it, our sphere only had 1 option. So its m sub l value could only be 0. Only had 1 orientation. On the other hand, when we had our L equals 1, we had m sub L of -1, 0, and 1. And you can kind of imagine that each one of these corresponds to that orientation. Right? -1, 0, and 1. And so that's what our m sub L is telling us, is it's basically giving us what orientation to take on. And so it will stretch from one value all the way to the other. So the higher your L goes, then the more m sub L you need to discuss it. So for our L equals 1, these are called our p orbitals. And there's 3 of them. They basically look like they have 2 lobes. And they are said to have 1 node. That basically there's kind of 2 sections for each one. One is to the left, one is to the right, or the top and the bottom. But basically, it's like our 2 balloons coming together. And so that's what we're looking at. Our next one is going to be when L equals 2. So L equals 2 is for our d orbitals. So our d orbitals, if we have L equals 2, then we must have 5 different orientations for it, because our m sub L should be able to go from -2 all the way up to +2. So -2, -1, 0, 1, 2. So these take on a different shape. They're going to be our 2-lobed, or they're going to have mainly 4-lobed, but one of them is 2-lobed. But basically, they're going to look a little bit different than our other ones. And so they're defined actually by being in these planes. Now, you don't have to worry about memorizing these, in the sense that I don't need you to worry about the different orientations of the D, but I do want you to know what they look like. So our d orbitals, this is L equals 2, right? We have our 5 different shapes. We have -2, -1, 0, 1, 2. Right? Now, these values don't correspond directly with those orientations. You don't have to worry about that part. But you can kind of see that these look a little bit different. Instead of being the dumbbells, they're really in a plane, and there's 4 options for how they take on. So our d orbitals are a little bit more complex in their shape. The last one that we have to worry about is what we consider to be our f orbitals. So these are our L equals 3. Now, just like how d orbitals had more options than p orbitals, and p orbitals have more options than an s orbital, f orbitals have our most options that we're going to worry about. Right? It has a total of 7 orbitals. So when we look at it, our f's are much more complex in their shapes. There's also a lot more of them. Right? We have kind of this 2 dumbbell looking one with the rings, right? We have a couple of different other ones with the rings. We have these very involved orientations. So we don't have to worry about drawing our f orbitals or our d or our p or our s, but we do want to know what they look like, and sometimes I think the visual of their shapes help us remember. So when we describe an orbital, there's kind of 3 things that we need. We have to tell us, well, what energy level is it in? So that way we know how far or close from the nucleus it is. We need to tell us the shape it is, and then we need to tell us the orientation. So orbitals with the same value of n, they're said to all be in the same principal energy level. So all in that same shell. N sub L are all said to be in the same sublevel of that shell. So when we looked at these ones for our P grouping, all 3 of these are said to be in the same subshell if they all have the same N. because the L is also the same. Now, when we talk about those, what we want to remember is not all of those values of L exist for all values of N. So our S group is in everything. It starts at N equals 1. But things like our P grouping, it only starts at N equals 2. Our D only at N equals 3, because you have to remember L can only ever go from 0 up to N minus 1. So we're always 1 behind. Now, when we were looking at all of these shapes, what we didn't talk about was that it doesn't matter what orbital you are, whether you're S, P, D, or F. Each of these orbitals fit 2 electrons. That's the most that they can fit. One's going to spin positive, one's going to spin negative, and we'll talk about that in a second. So when we try to fill them in, our S grouping, it's got one option, right? It's our first subshell. It's only got one orbital, which means that it can only fit 2 electrons. P has M sub L of -1, 0, and 1. So that gives us 3 orbitals, which is where we get our 6 electrons from. So if you can remember how many orbitals you can make, you can tell how many electrons fit in. Or if you remember how many electrons fit in, you can tell how many orbitals there are. So our periodic table is set up to help us with that. When we look at our periodic table, the way that it's grouped up is these two, our alkali metals and alkali earth metals, are our s orbitals. And you can kind of see that they only hold 2 electrons as you work your way through. Our p group is the main group elements. And it's this block over here. And if you count your number of columns, you have 1, 2, 3, 4, 5, 6. You have 6 electrons for that p group. Our transition metals are our d group. And if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So 5 orbitals. And down here at the bottom, the lanthanides and actinides, this is going to be our F group, or F block. And it's got 14 electrons. So you can tell how many electrons you have by basically how many orbitals, and you can use your periodic table to help you remember how many electrons and how many orbitals they can fit in between. You just have to remember about which subgroup is located with which one. So this is kind of like a diagram to help you remember that part. Right? When you're looking at it, n equals 1 only has one option. So it's only got one grouping from our sublevel. Right? So when n equals 1, L has to be 0, and our M sub L can be 0. When we move up to our energy level, so n equals 2, then we have 2 options. And so we could be either a 0, which is that 2s, or we could be the 1, which is our 2p. So there's that relationship between them. N equals 3 now has 3 different options. And so you can see how many more options we have inside of each. Now, this chart is basically all of them put together for each of those energy levels, right? N equals 1, N equals 2, N equals 3, and N equals 4. And so this is just to help you visualize as you go through what it looks like. You can see that every energy level has one value where it's your S1, where they all have 0. You can see that for N equals 2 on up, they all have a P value. For N equals 3 on up, we get those D blocks. And then for n equals 4 on up, we get those F blocks. And so we do want to know the number of orbitals. So you do want to know your number of orbitals. And you do want to know your number of electrons. Now, when you combine all of these together, what you'll see is that those different orbitals, the reason why they take the shape on that they do, is that it looks something like this. So the first option that we did, that sphere, when we first have them, they can be anywhere inside of there. But as we go through, we start to think about where they would have the least amount of interaction with each other. And so that's how they kind of start taking on those different shapes. You can see our P groupings, the shapes that they try to take on, is so that way they minimize their interaction with each other. Once that's there, then our F groups kind of try to fill in, or sorry, our D groups try to fill in those gaps in between those from the S and the P. Once those D groups are in, then the F tries to squeeze itself around on the outside. And so overall, when they're all in there, it kind of looks like a sphere. But each of those individual shapes is because they're trying to minimize their interaction with each other for their electrons. Because our electrons repulse other electrons. So they want to be as close to the nucleus as they can get, but as far away from each other as they can be. So that's our first three quantum numbers. We have N, we have L, and we have M sub L. But all electrons, in order for us to talk about where they are located and what energies they have, there's actually a fourth quantum number that we need to add. And it's called MS. And we're going to talk about what that is. So for our orbitals, they generally have what we call a phase. They have either positive or negative values associated with their wave function. Now, since we look at our wave function as being squared, we only ever see the positives. But that value could have been either positive or negative for that individual electron. And so this is called its phase. Now, they could be the same sign, they could be opposite signs as they interact. And so what we're looking at is whether they're going to be a positive or a negative. You can kind of see our 1s versus our 2p. Now, the way that we see this with electrons is something called spin. And so we were able to show that when we sent a stream of electrons, some of them would spin positively and some of them would spin negatively. Some of them would go like north and some of them would go south when we would put them through a magnetic field. And that spin is going to be what we use for our last quantum number. That M sub s that I was talking about, that's going to be our last. Our M sub s is going to be our last quantum number. And it's going to talk about specifically which of those electrons we have. So all electrons have a spin. And they all have the same amount of spin. The only difference is one of them is going to be what we call spin up. One of them is going to be called spin down. So this doesn't show up in Schrödinger's equation because his equation has them all being, we square it at the end, and so it becomes a positive. And so Schrödinger's equation doesn't account for it, but we do see it as a physical representation. So the values of MS are either going to be a positive 1/2 or a negative 1/2. And the thing about it is we don't actually know which one an electron is going to be, but we do know that if we have two electrons in the same space, one of them has to be positive 1/2 and the other one has to be negative 1/2. So when we start drawing out diagrams where each square represents an orbital, then that orbital can fit two electrons in there. One of them will be spinning up, one of them will be spinning down. When that happens, we call those electrons paired. Right? So this is an example of an orbital diagram that is paired. We have a spin up and we have a spin down. You can do them with full arrows as well. That also works, but you can also do them with half ones. And so this is kind of the idea between how they spin. One spinning north, the other one spinning south. Right? So one spinning to the right, one spinning to the left. So our quantum numbers have four things. We need the N, we need the L, we need the M sub L, and we need the M sub S. Now helium has 2 electrons. Oh, sorry, reading ahead. Helium has 2 electrons, and both electrons are in the first energy level. So both electrons are in the s orbital of the first energy level. And because they're in the same orbital, then we know that they have to have opposite spins. So if we wanted to draw that out, our helium looks like this. It's going to have so many electrons in its first orbital. Its diagram will look like this. And those quantum numbers, this could be electron 1. This could be electron 2. The quantum numbers, they're both in our 1 energy level. They're both in the s orbital. That s orbital only has one option, so they're both losing that same m sub l, but one of them is going to spin up, one of them is going to spin down. And so you can kind of imagine that this is kind of like talking about that one, and this is kind of talking about that one. Now, we don't really know which one came first, the positive or the negative, but that's how we can tell the difference between them. Now, the reason why we have these different orbitals is because they are taking up different spots. But what's important to remember is that sublevel splitting, so that means that things with the same value of L and the same value of N, no, not N equals L. They're what we call degenerate. It means that they have the same amount of energy compared to each other. So whether you're in the first one, the second one, or the third one, for your orbitals, they would all have the same amount of energy. So we kind of split those up across all of those different sublevels. Now, what is different though, is that L is lower, or not L, S is lower in energy than P, which is lower in energy than D, which is lower in energy than F. So your L value, the higher your L value, the more energy that sublevel has. So I'm going to show you a diagram that kind of splits that up for us. So let's imagine that we have just one N, right? Our energy level equals N equals 1. So that's here. So our first energy level, when we have it, it only has one orbital, and so all of them are at the same value. When we move to that next level, N equals 2, N equals 2 has 2 values of L. Our L can be 0. It can also be 1. And so that energy gets split. There's some amount that's lower than that. That's the L equals 0. There's some amount that's a little bit higher than our N equals 2, and that becomes our 2p. When we move to N equals 3, it becomes even more complex. Now we have L equals 0, we have L equals 1, and we have L equals 2. So it's become even more involved for that process. So as we go up our energy level, the pictures kind of become more complex, right? We get more and more splitting. When we get to N equals 4, we get even more splitting between them. N equals 4, we get L equals 0 all the way down here at the bottom. I'm going to switch my color up so you can see it. L equals 1, L equals 2, L equals 3. So it gets even more involved. So our energy level splitting, not all of those electrons at the same energy level, N, so not all of them with the same N value have the same amount of energy. But if they're the same N and the same L, they have the same amount of energy. So all of our 2s is kind of involved in the same energy state for now, right? 3s. That gets a little bit more specific a little bit later on, but for now we can keep those. Okay. Now, as we're going up, One thing to remember is with each of our energy levels, as our n increases, the gap between energy levels gets closer. So N1 to N2 is larger than N2 to N3. And this is why as we get higher and higher up, we see more mixing of our values, right? In this case, our 4s is really lower in energy than our 3d. So it does complicate things as we start to fill in. Right? And this just has to deal with the fact that as you move farther away from the nucleus, our energy levels, their distance becomes closer together, and the energy difference between them becomes closer together. So in general, when we fill in our electrons are going to be lazy. They're going to follow a Fabauer's principle, which is basically electrons fill from the lowest energy orbital first. It's sometimes called the lazy tenant rule, in which case, when you first are to move into an apartment, you're going to take the first room that's available. You don't want to go up all of these steps to get to higher levels. You're going to take the first one. So if we were to look at one of these, as we fill in, the first electron would come in here and go into that 1s. Our second electron, it still has space in that 1s, so it would fill in next to it. Our third electron is going to come up. It can't fit into the 1s, so it's going to go into our next available one. So it's coming up here into the 2s. Fourth available, fifth, right? And so on. So we're always going to fill from basically the bottom up, or your lowest energy on up. Right? So that's how they fill in. And so that's our first rule. The second one is Hund's rule. And so within a sublevel, all of our electrons are going to take their own orbital before pairing up. And they kind of call it the empty bus seat rule. And it's kind of like what you see on BART. When you first get on BART, if there's 3 chairs, people don't sit next to each other first off, right? They don't sit paired up. Instead, everyone kind of takes their own seat as you go in, and then only at the last resort do they start to pair up. So if you imagine this, if we have 3 rows of our seats, so our 3 orbitals, the first person that comes in takes one of them. Second person comes in, takes their own row. Third person comes in, takes their own row. And now that fourth person, when they come in, now they can't get their own row, and so they are going to partner up. And then you would go on until everyone's all full with our 6 electrons. Right? So we fill from the bottom on up. We also all try to take our own orbital before we start to share. And then the very last rule, Pauli exclusion rule, means that any orbital can fit 2 electrons, but those 2 electrons have to have opposite spin. So you don't ever want to put 2 up ones together. That doesn't work out. You can't have that. So they have to go from one to the other. They have to be one's positive, one's negative. You can't have them both spinning in the same direction. Now, there is a worksheet that's going to have you guys practice doing your orbital diagrams. And so I've linked that into your slide for today. And so I would definitely recommend practicing that. Right? You want to work your way through, practice filling them in so you can see a little bit what that looks like. And you can get a little bit of practice doing that part. That worksheet, the answers for it are going to be on slide number 77. Right? So we're going to go through that worksheet and we'll do some practice problems, but now is a good time to start looking at that worksheet. I'll do this in a better color. So the worksheet, and then your answers on slide 77. So there's two ways to kind of think about how they fill in. Now, this is like a little bit of a cheat sheet for how it works through, right? And what you can do is you can list all of your options. So you can see how this is all n equals 1, and this is n equals 2, and this is n equals 3. Right? And so as you work your way through, we're always going to start with our top one first, and we're going to fill in accordingly. Now, it follows in this line and like this. Right? 1s, then our 2s, then our 2p into our 3s. And the reason why we need to use this one is because of that mixing. Because our energy levels get closer, there's times when we're not going to finish all of our third energy level before we go into our fourth. That's because the 3D has more energy than our 4s. So we got to do the 4s first. That jump happens again with our f's, right? You can see that we're actually going to fill in our 6s before we do our 4f. And so this setup kind of helps you remember how that works out as you fill in those electron configurations. The only part that I don't like about it is that this one is just all memorization for this method. It's a lot of pressure on you to remember all of it instead of having you use your periodic table to help you out. Right? So we're going to do some practice ones. You can use this method if you want. We're going to do a little bit of practice, and then I'm going to do it with the periodic table, and then we'll do some more practice so you can kind of see how that works. So the first one that we're going to look at is we're going to look at hydrogen. Now, hydrogen has one electron, and so that first electron should come in here down at the bottom, very bottom, our 1s. Bam. Right? If we look at helium, then our helium is going to have 2 electrons, and it's going to fill in from the bottom. Now, as we write this, we're going to start to fill in what we call as our electron configurations. Now, electron configuration kind of has 3 parts to it. And to do that, we're going to do the whiteboard. So for our electron configuration, the first thing that you want to do is you want to write down what your n value is. So for hydrogen, our first energy level was in our 1. Then from our n, we're going to talk about our shape. And so the shape should be our first orbital. So this is going to be our s, right? So that's kind of our when L is equal to 0. And then this last part is going to be how many electrons. So we have our n value. We have our L value. And then we have the number of electrons. Right? And so as we go through, that's how we're going to fill those electron configurations. So when we go back, we look at our next one. We're going to look at our helium. And so our helium has 2 electrons. And so I want you to take a moment. I want you to write out what you think your electron configuration should be for helium if it has 2 electrons. From there, we're going to move on to lithium next. So you can try that as well before we move on into that next part. So helium is going to be 1s2 because it's got 2 electrons, and both of them are in the first energy level, the s orbital. Lithium looks a little bit different. Lithium has 3 electrons, and so the third electron is coming up into this 2s. And that's because there's no more space for n equals 1. So its electron configuration, those are our first 2 electrons, and this is going to be our third. So we should be able to do that as we fill in. So the next one we're going to look at is carbon. So take a moment to your carbon. So carbon has a total of 6 electrons. So it's going to fill 2 from the bottom, 2 into 2s. And then the next part is we want to make sure that we split our 2p orbitals, right? Remember 100. Sorry, went a little bit too far. And so we should have each inside their own orbital. Now our electron configuration should be 1s2, 2s2, and 2p2. Now, as you go through this, make sure that when you write your 1s2, 2s2, 2p2, all of these, actually, let's make them a different color. All of these need to be superscript. What that means is they should all be a little bit above, and they should be a small number. The format on this is very particular, right? What you don't want is something that looks like this. Right? Because when it gets there, then I don't know, is that a 2s or is that a 22s? Right? I'm not sure how that works out. You also can't just leave it like this. You have to include the 1. Right? You can't just cut that part out. So you want to make sure that you have that set up, that you have those formatting the correct way, because those are easy points to lose and they're easy points to gain, right? So you just want to make sure that you're practicing writing them out in the correct format as you go through it. So the format is very particular. Right? The other part is don't do things like this, right? No commas. All right, very good. You should be able to try your nitrogen as well. We should have all 3 of those split, just like we had in Hundrel. And then we're going to jump ahead a little bit. We're going to try to look at this aluminum one. So aluminum is a tricky one. Aluminum, we should have our 1s2, our 2s2, our 2p6, 3s2, and then we should jump across the periodic table over into that 3p1. And so our aluminum should be looking something like that with our finish of our 3p1. Now, electron configurations is one of those things that you want to just keep practicing, right? And so there are some more of those up there. You want to practice working your way through those different electron configurations. We're going to look at the next section now. So the names of your notation, orbital diagram refers to the boxes, right? So it's when you have your boxes and you're trying to indicate where your electrons exist from. The electron configuration is when you write it out in this form. Now for the notation, the electron configuration, sometimes we talk about it in 2 ways. We talk about inside of its longhand notation or longhand configuration. And so that's when we write it all the way out. And you can check, we should have 16 electrons here. So we have 2, 4, 10, 12, 16. So we have all of them accounted for. But what we can start to do is we can start to split these between what we call core electrons and valence electrons. Now, valence electrons, these are in the outermost energy level. So they're your highest n value. And so what we can do is we can simplify this. We can do what we call the shorthand configuration, in which we take all these core electrons and we summarize them with a noble gas. I think that should be noble gas. And so you can see that this 1s2, 2s2, 2p6, if we were to look at that electron configuration, it would be the same as neon. Neon is equal to 1s2, 2s2, 2p6. And so if we wanted to, we can use these brackets. We can put in neon. And so we're kind of saying that these electrons are just like neons. Plus, we have the valence electrons on top of it. And so the important part with your shorthand configuration is that when you use them, right, it can only ever be noble gases. So that means it can only be helium, neon, argon, krypton, xenon, radon, right? You can't use any other elements. The second part to remember about them is it has to be brackets, not parentheses, not the funky little squigglies, right? Has to be brackets. So if we wanted to take this and change it out, you can take that neon, put that in place. Looks like this sodium, because it's really 1s2, 2s2, 2p6, and then the 3s1 on top of that. So this is its electron configuration, and then these are going to be its breakdowns. Now I'm going to erase our ink, and then we can go. All right, so A is going to be kind of your noble gas electron configuration. Your 3 stands for your energy level, so your N. Your D is your orbital shape. And that 1 stands for that there's 1 electron in that s orbital. So this is kind of the format as you guys work through. On the next one, what we're going to look at is I want you to try out how you would find it for krypton and also how you would find it for rubidium, Rb. Once you have those, then we're going to move on to the next slide and we'll walk through those. So do it for krypton, do it for rubidium. So krypton, it has a total of 36 electrons. So we need to start all the way at the bottom, that 1s2, and we're going to build our way up until we have 36. So we go 1s2, and then we move down to the second level, so 2s2, 2p6. We still have more electrons to go, that's only 10. So we have 3s2, 3p6. And then normally we would go right into our, oh, sorry, let me fix that. Normally we go into 3D. But if we look, we know that 3D actually has a higher energy than our 4s, so we're actually going to go into 4s2 next. Right? So we've used 2, 4, 10, 12, 18, 20. We can still do all of 3D10, and then we'll go back to finish off our 4p6. So at this point, we have 36 electrons. So that's kind of how we can work our way up. So you want to make sure that you had this part, the jump between 3p to 4s, and then you went back down to finish off your 3D. Right. Rubidium, we should have another jump, right? We should go from our 4p over to our 5s as we go through. Now, if we wanted to think about those quantum numbers, for that 5s1 electron, we would define that as our n is equal to 5 because it's in the 5th energy level. The L is equal to 0 because it's an S. ML is going to be 0 because there's only one option of ML. And so our MS, we could actually have that as positive 1/2 or negative 1/2. But in general, when it's the first electron, I like to say that it's just going to be positive. It makes it easier for me. And then I could say the second one is going to be a negative 1/2. Now, for that same element, we could also talk about an electron in that 2p sublevel. Now, we know its n value. Its n value has to be 2. We know that L has to be 1 because this is talking about the p. Right? But what we don't know is what value the m sub L can be. Right? Because there's 3 values there. So it could be really any of those 3, -1, 0, or 1. It could also be either of these 2, -1/2 or positive 1/2. So if they just list all options, then they want all of those values. If they list a option, then you can choose one value that's correct. So if it just says list an option, then go ahead and do either -1, 0, or 1, but just choose one. And you can do -1/2 or +1/2. If it says list all of the options, then you have to include -1, 0, and 1, -1/2, and +1/2. And so that's the difference between them. This slide right here, you're going to work through and you can practice going through what element symbol should match with those electron configurations. So I'll give you a moment so you can practice those. If you see any mistakes in your electron configurations, then go ahead and fix, oh, it's a highlighter. Go ahead and fix any electron configurations that are incorrect. So I'll give you a moment now. So our first one should be calcium. This one should be argon 4s2 3d3. This one should be fluorine. This is silver, so this should be our 5s2 4d9. Iodine is going to be 5s2 4d10 5p5. Xenon. Now this one is iron, but we do need to fix that one. Instead of being what it was, it should really be written like that, argon, if we're going to do it. And this seaborgium, we can write like this. Now, a good way to check, right, is look at your number of electrons. Like for some of these long ones, when they kind of get up there, iron has 26 electrons. So we know that argon is 18. We have another 2, 20. We have another 5. So that's going to give us 25. Or 18, 20, 25. And so we're actually missing an electron. So this shouldn't be 3d5. This should be 3d6. And so that's how you can catch a mistake. The same thing we can check for SG, seaborgium. It's got 106. Now radon is 86. So 2 more, 88. 14 is 104. And so, no wait, 86 plus 14 plus 2 is 102. And then 5D, so we're adding up to 106. And so that's ways we can check. Now, some of these are not all correct. right? In the sense that, sorry, silver here, it falls into a category called irregular electron configurations. And so we are going to worry about that. We are going to have to know our irregular ones, but we're not going to do that this week, right? Right now, I just want you to practice doing them like they normally would be. And then next week, we'll talk about the irregular ones. The other one is, as you go through, why I was trying to go back, is that when we look at this one here, xenon, you can't just write this as xenon. Mm-hmm. You always have to use the noble gas from one before it. So you can't just write it as xenon. It has to be the one right before it. And so you just want to be careful with using that shorthand for that one. And then we have those all set up. Okay. You can practice these as well, right, as you work your way through. What I would say is count your number of electrons, and that's kind of one of your fastest ways to tell what you should be at. So I'm going to give you a moment so that way you can work your way through and figure out what element each of these stand for. There we go. And then for our next one, let's go ahead and instead of address, we're really asking for what's my electron configuration. Now you can either do this shorthand or longhand. I would definitely recommend doing your longhand so that way you can practice even for some of these really long ones, right, as you go through. So go ahead and take that moment, work your way through now. And then that's what your electron configurations look like. Now, for our class discussion, what we're going to be using today is this is going to be our attendance survey. And so you want to go over to your discussion. Right? And in your discussion, we're going to have the ability to look at completing this electron configuration. So if we look at our class, our module, for today's lecture, so now we're in week 9, we're going to be able to click on this electron configuration discussion, and it's giving you what you need to do. So your first step is you want to go ahead and respond to this thread. Did I cancel my share? No, we're still good. Okay, just making sure. So our first step is we're going to do our electron configuration discussion. The first one is do the longhand of the element. And so you can make your reply down here, and you can do the longhand of that element. And you want to do that by Thursday. Once you have yours up, then you can respond to someone else's, and you're going to take their longhand and you're going to make it into the shorthand of it. So if I wanted to start this out, I might write out 1s2, 2s2, and that can be my element. Right. Now I want to make sure that I superscript the numbers that need to be. And so that's how I can start it out. After that, you could respond to that thread by adding in their shorthand. And then you would respond to someone else's where you convert that shorthand into the number of electrons. And then the very last thing that you need to do is convert someone else's from their number of electrons to what element name that would be, right? And so this is electron configuration telephone. And so we can work our way through this and we can see how good of a job we did. Yeah? By the end, our element should match up with what we started out with, but we want to practice each of those individual steps. So that's kind of what's going on for our class. So this is going to be what we do for our discussion survey. And so you want to make sure that you do this, start it by Thursday, and then all 4 steps done by our Sunday. So go ahead and you guys can work your way through those. Now, normally in class, we would have done it as like a telephone. You guys write it down on a piece of paper, but I just want you guys to practice this part as well. Now, we talked about our valence electrons. We talked about our core electrons. I just want to make sure that you have this there so that way you can really reinforce which ones are which. So valence electrons are always the ones with the highest N. Core electrons are anything with a lower energy shell than that. Our valence electrons are generally more involved inside of our chemical reactions. And so later on, we'll see why they become more important. Now, I'm going to teach you how you can use your periodic table to help fit you with those blocks. And so that way you can also work on using this instead of the method of memorizing all of your 1S's in what order they fill in. So your periodic table looks like this. When you see this, you can go ahead and take your highlighter and this section over here, right? This is our S block. And these rows are our N values. So as we start from the top and work our way down, the first row is going to be N equals 1, N equals 2, N equals 3, N equals 4, N equals 5. Yeah. So you can see all of your N values from where they fill in. This grouping over on this side, this is going to be our P group or P block. The only one that's not there is helium. Helium is actually more like it belongs right here when we talk about electron configurations. This group, just like we had talked about earlier, is going to be our D block. So our transition metals is all of our D block. And so this is all things that end with a sublevel of D. So when we first look at those, 1s and our 2s, you can kind of see how they fit in as we work our way down. We have our 1s1 for our hydrogen, 1s2 for our helium. Nitrogen is 1s2, 2s2, and then it's the third one inside of that P group, so 2p3. So you can use this to kind of work your way through all of your electron configurations. You can kind of see that where our beryllium stops, then that means that we have to transition to our next orbital when we move on to boron. And that corresponds with this jump between our beryllium and our boron. You see that where neon stops, we're kind of at the end of the row, and so we're going to move on to our next energy level as we go back between them. Now, we did have an adjustment, and so we do have to pay special attention to this grouping here. When we move into the D block, there's going to be a shift down. Our N is going to subtract 1 from the row that it's on. So instead of this being 4D, this is really our 3D. Instead of being our 5D, this is our 4D. And so they all come down by 1. They're all 1 less than where they should be. So this is kind of like our blocks that we've put them in. And so now you can kind of see how they fit in there. We have our S block, our P block, our D block, and then the very bottom that all gets grouped in our F block. Now, F block, you can kind of see on your periodic table where it fits in there. And you can do that by looking at your electron count. So if you look at where those electron numbers are, you can see where they should fit in your periodic table. Right? And so our periodic table looks just like this one. Lanthanum and actinium, sometimes they're included in this series, sometimes they're not. And so you do want to pay attention to what that means. Right now we fit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we can 14 in here. And then we can fit 10 over there. Right? And so you just want to pay attention to that part. Right? Different periodic tables, draw them as slightly different. And it just depends because our lanthanum and our actinium are kind of like irregular ones. Instead of going into our Fs right away, they really go into our Ds. And so they can become a little bit tricky as you work through them. So you do want to pay special attention to your F group. So in our periodic table, this one is set up with all of their electron configurations underneath. So you can kind of see what kind of trends they fall into. You can use that as you work your way through. Now, a couple of weeks ago, we had classified things into blocks. We had classified our groups as having similar chemical properties. And you guys did an experiment where you kind of tested things out with our oxygens, right? The oxides. We looked at which ones were metal, we looked at which ones were non-metal, and we kind of compared those. Now, you can see that for those groups, not only did the chemistries look the same, but their electron configurations start to look very similar. So elements in the same column have similar properties, and that shows up again in their electron configurations. So the quantum mechanical model starts to explain why. And it's because the number of valence electrons and the types of orbitals that they occupy show up periodically. So we start to see that things like noble gases, the reason why they're so stable is that they all have these valence electrons, but those valence electrons correspond with having a complete p orbital being filled. Makes it hard for us to remove or take away from them. Our alkali metals, on the other hand, they're very reactive because they all have just one extra valence electron hanging out in their S, in that next level of their energy levels. Whereas our halogens, they're all ending in this P. They're working so hard and they're so reactive because they're trying to get from that 4p5 to that 4p6, right? Or from that 3p5 to that 3p6. They're all trying to work so hard to fill theirs in. So make sure that you practice drawing out your orbital diagrams, right? So this is the worksheet that's online. This is going to be your answer key from it. Just make sure that you also pay attention to all three of the rules, right? We want to make sure that we're starting to follow Hund's rule here. Separate them out. Don't stack, don't pair them until every open orbital in the energy level gets one. Right? And we're going to use that as you move forward. The second part is for our ions, our anions or our cations. We're looking at how they kind of form. And so you can kind of think that, well, an S2 anion is basically an S atom with 2 more electrons. And so they're going to put those in the 2 next available ones. So if this was our S, right, going up to 3p4, then if it gained 2 more electrons, those 2 would go into its p orbital in the 3rd energy level. And so it would become 3p6. When we look at our cations are pretty much just like where they're coming from. But like this one for our magnesium 2+, that means it's losing 2 electrons. So it's going to lose its 2 valence electrons, so the ones that are in its highest energy state. And so they become 2p6 instead of 3s2. And so that's how you can adjust your electron configurations for their ions, right? So you want to pay attention to how the ions are working. Now, the very last thing that we're going to cover for this class is we're going to talk a little bit about Coulomb's law and its effective nuclear charge. So Coulomb's law is up here. And these Q's are your charge. So one's the charge of one ion, and Q2 is the charge of the other ion. So Coulomb's law is kind of this attraction or repulsion between the charged particles. The more negative your charge is, then the more attraction there is. The more positive, the more repulsion. So when we look at our Q1 and our Q2, they're being compared against their amount of charge that they have for each other. Right? So a positive 2 charge is more strongly attracted, so electrons with the negative 1 charge is more strongly attracted to a positive 2 charge in the nucleus than the positive 1 charge. Right? And that's because Q1 times Q2 goes up, right? -1 times +1 is only a -1. -1 times a +2 is twice as strong. This R term is our radius. So that's how close they are to the nucleus. And so as our energy levels get farther from the nucleus, they're not as negative because their Coulomb attraction is weaker. So they become more positive in their energy. So they have a higher energy because they're not feeling as negative of a charge from the attraction. And all of this is just a constant. So the idea is that as we look at our charges and our radius, we can start to decide what kind of impact or how attractive or repulsive they should feel. And so this gives us 2 terms. We get shielding and we get effective nuclear charge. Now, shielding is the impact that electrons have on each other. So when we have multi-electron atoms, then they're kind of experiencing this attraction to the nucleus, but they're also experiencing this repulsion by other electrons. Right? So they are trying to work between those 2 things. So these repulsions, they reduce the attraction to the nucleus because they shield it. They kind of block it from the other. On the other side, an electron that kind of feels that, it's seeing this difference change in the nuclear charge that it will see. Instead of being like a 3 for its nuclear charge, it might see a little bit less than that, 2.75. And so that effective nuclear charge is what we're trying to do to take into account the amount of attraction that it does see. So the way that shielding works is outer electrons get shielded by the core electrons. So if you are on the outer side, then you're kind of getting screened. And so the outer electrons are not affected, so they can't see the nucleus as well. However, outer electrons don't screen each other. So if you're in the same n level, then you don't screen each other. And that shielding means that those electrons on the outside don't feel that full effective strain. So overall, we're going to just do this first so that way you can kind of see a picture and then we'll go back to the trend, right? Is that if we have a nucleus of this 3+, these electrons in here, they can see all of that nucleus. There's nothing in the way blocking them. But this electron, the one that's out here in an outer level, the valence one, it doesn't see as much of this nucleus because sometimes these electrons are in its way blocking its piece. So those core electrons end up shielding that nucleus, blocking some of it from that one on the outside. Now, if we could move it to the middle, it would experience that full 3+ charge. If not, when it's out here, then it's shielded. And so different orbitals will feel different amounts there because some of them can have a higher penetration than others depending on their shape. Sorry, I shouldn't be using yellow. So they're shielding, right? If they have different penetrations, it's because of their shape or the L value. So when we look at our effective nuclear charge, your effective nuclear charge is generally a net positive of attracting a particular electron. And so you take your Z, your nuclear charge, which is the same as saying your number of protons, and you subtract from it all of those number of electrons inside the core electron. So this is going to be a simple way for us to get a Z effective. Now, if they're in the same energy level, we don't have to worry about them. And so that's how we can get this Z effective is Z minus S. So when we look at this one, its effective charge was Z equals 3. It had 2 core electrons. And so that's how they could figure out its effective charge was going to be a +1. In general, the trend is S has a greater effective nuclear charge than P. D is greater than F, right? So S, P, D, and F is the trend for that, and that has to deal with their penetration. Right? The lower your letter is, right, your shape, then the more it can kind of move into that lower energy levels compared to the other ones. So that's the difference between shielding for different levels as we move through them. And so the things that you want to practice is you want to practice your electron configurations. You want to practice your quantum numbers. You still have your energy of a photon. You have your energy changes of your electrons. So we kind of have a lot going on through there. Conceptually, it's nice to know about this idea of effective nuclear charge, your shielding, right? Your shapes, but we're going to get into that a little bit more. So practice those 4 things first, and then once you feel comfortable with those, move on to worrying about effective nuclear charge, your shielding, and that part. Effective nuclear charge helps us explain a lot about the periodic trends, which we're going to get into on Thursday, but you do want to be practicing this. All right? Good luck.